Hello everyone, this is the second video on discrete random variables. In this video, we discuss the definition of discrete random variables and probability mass function, which is also called probability distribution function of a discrete random variable. A random variable is called a discrete random variable if its set of all possible outcomes is countable. Let's consider this experiment. Two balls are drawn in succession without replacement from an urn containing 4 red balls and 3 black balls. Let X denote the number of red balls. Let's write all the possible outcome of this experiment. Since two balls are drawn without replacement, the possible outcomes can be BB, that is two black balls. Both the balls can be black. One can be red, other can be black, and both can be red. And XP, the random variable, we can associate a real number to each and every outcome. If the random variable is number of red balls, therefore we can associate a real number 0 to BB because it has no red balls, and real number 1 to RB, and real number 2 to RR. Thus, random variable X has 3 elements 0, 1, and 2. This is an example of discrete random variable. Now let's define the probability mass function. For a discrete random variable x, we can define a function that assigns to every x in x a probability of its occurrence, and it is called probability mass function. Let's see this example. Let me consider one random experiment whose possible outcomes be S1, S2, S3, S4, S5. Okay, this is enough. Now assume that each and every outcome is equally likely to occur. If that is the case, the probability of occurrence of S1 is equal to probability of occurrence of S2. This is equal to probability of occurrence of S3, that is equal to probability of occurrence of S4. S5, that is equal to 1 divided by 5. And now XP is random variable. It's defined as given here. What we do here is we assign a real number x1 to s1 and assign a real number, the same real number x1 to x2 as well, and assign a real number x2 to s3 and x3 to s4 and x3 to s5 as well. Okay. In this case, we can say the random variable has 3 elements x1, x2, and x3, and we can assign a probability of occurrence to each and every element in this random variable x. Why? Because these are images of sample space. Now we can say the probability of occurrence of x1, this is nothing but its pre-image is S1 and S2. You can write this as S1 and S2. Since both S1 and S2 are equally likely to occur, this is equal to probability of occurrence of S1 plus probability of occurrence of S2, and both are independent. Assume that. Okay. We get this because occurrence of S1 and occurrence of S2 are independent to each other. We write something like this. Probability of occurrence of similarly x2 is equal to probability of occurrence of S3, right? S3, which is equal to this is 2 by 5, above this is 1 by 5, and probability of occurrence of S3, this is equal to a probability of occurrence of S4 or S5, this is equal to 2 by 5 again. And thus the probability distribution of the random variable x is given by this. If x is a random variable and probability of occurrence of each and every element in x is this, it's 0, 1 and 2 is 2 by 5 1 by 5 and 2 by 5. This is how we denote it. And this is a function. Thus this function is denoted by p of x, because x is the variable and random variables, and this is a probability function defined on the random variable x. Therefore we denote this by this p of x. Okay. And that is let me show this pictorially, and let's see this. Each and every sample space elements in the sample space is assigned to some real numbers. Sorry, real numbers are assigned to each and every element in the sample space. In turns, real number from 0 to 1 is assigned to each and every element in this random variable. This is a probability mass function, and this is given by this. In general, which is defined by this probability mass function p of x, which is same as probability of x is equal to x, is nothing but probability of all those elements in the sample space whose images are in x, or images are is x, images is x. And it's worth to note this: the sum of all these probabilities is equal to 1, because from the property of probabilities, it's clear that sum of all the probabilities of a sample space is equal to 1, and each and every probability is greater than or equal to 0. The same property can be written for the random variables as well. The properties of this: the probability mass function is greater than or equal to 0 for all the values of x, and sum of all the probabilities of random variables is equal to 1.